Welcome back, grade 12s. I hope that you did the pretest and that you marked the pretest. And I actually do hope that you find a few things that you aren't quite sure about. But don't worry, now we're going to get on them. So the first topic that we are going to revise is going to be organic chemistry. Now guys, a lot of what you're going to see today is going to be old news. Why? Because these are important. The definitions I'm going to give you today, the things you have to be able to do, the rules you have to follow, all of these come straight out of your exam guidelines. Please, grade 12s, make sure that you have your exam guidelines. Your exam guidelines tell you exactly which definitions to know. It tells you exactly how questions can be asked, and it also contains the mark allocation for each topic. This means that you will have a very, very good idea when you go into your final paper of what to expect. Right, so let's have a look at organic chemistry. So guys, we're going to start with a few very basic definitions, but you're going to see in just a moment why I put so much emphasis on them. The first definition that you have to know is the definition of a homologous series. Now please be very, very careful. Do not confuse homologous series with functional groups. Although they are very closely related, they are not the same thing. So a homologous series is a series of organic compounds that can be described by the same general formula. Now, a handy hint if you struggle to remember, a homologous series all have the same functional group. And this is why we need to know the definition of functional groups. This is quite an important one. A functional group is a bond, an atom, or a group of atoms that determine the physical and chemical properties of a group of organic compounds. So guys, I know, and I've seen this a few times in question papers, in the one question they'll ask you, which homologous series does this compound belong to? And in the next question they'll ask you, name the functional group. So please make sure that you understand the difference and that you practice these types of questions so that when you get to your final exam that you are very, very oiled in how to do this. The last definition that sometimes crops up is the definition of a hydrocarbon. Now guys, a hydrocarbon, the name says it all. It's a compound that consists of hydrogen and carbon. So this is a very, very easy 2 marks if they do ask this. But please note that you have to use the word organic compound and that you must include that it consists of hydrogen and carbon only. That is 2 very, very important concepts. Right, so now that we've sorted out what a homologous series is and what a functional group is, let me remind you of the different types of homologous series we get and their functional groups. Now guys, this one will look very, very familiar to you. I took this table straight out of the exam guideline. Okay? Again, guys, go find the exam guidelines for grade 12 physical sciences. It tells you exactly what you need to know. So, our first groups of homologous series are alkanes, alkenes, alkynes, and haloalkanes. For alkanes, we only have single bonds. Alkenes, we have a double bond, sometimes more than one, but you will generally only be tested on one double bond. And alkynes, which have a triple bond. Guys, if you struggle to remember which order these go in, I've got a very, very fun way to remember it. So if you look at alkanes, it has an A in the middle. And A is first in the alphabet. So first, single. So alkanes only have single bonds. Alkenes is the second vowel in the alphabet. So alkenes, E, goes with secondary or double bonds. And then, guys, I think the scientists got bored and they skipped all the other vowels that they had available to them right to the end. And I know why vowel, jury's still out, but this is the easy way that I can remember alkanes, alkenes, and alkynes, and which is single, double, and triple bonds. Then we have our haloalkanes, which is simply a halogen that is bonded to a saturated carbon. Now, guys, in grade 12, we are super fortunate. Any of our functional groups, whether it's haloalkanes or alcohols or anything further down the line, we are dealing with an alkane that has a functional group on it. If you choose to pursue organic chemistry further, you can get alkenes and alkynes with other functional groups, and then things get very interesting. But luckily, for grade 12, the only added that we deal with is onto an alkane. Right, so these are the first four we deal with. Then our next group of homologous series, we start having oxygens added to it. Now, guys, I apologize for the funny block, but like I say, this is exactly the way it looks like in your exam guidelines. So the first homologous series we're dealing with is an alcohol. So we have that OH group that is bonded to a saturated carbon. And that OH group is called a hydroxyl group. So if they ask you for the homologous series, it's an alcohol. If they ask you for the functional group, then they want the name hydroxyl group. Can you see how important it is that you know the difference? Right, next one is aldehydes. An aldehyde has got a double bond oxygen bonded to a primary carbon. Remember, primary carbons are bonded only to one other carbon directly. And that double bond oxygen on the primary carbon with its hydrogen is called the 4-mol group. Then we have ketones, and I always get confused with aldehydes and ketones. So again, I made myself a little story. An aldehyde, A, has to have the double bond oxygen on a primary, on the first carbon. And ketones can have the double bond oxygen on another carbon. It's not allowed to have it on the primary carbon. And when we have the double bond oxygen on a secondary carbon, we call it a carbonyl group. Now, guys, please be careful. They asked this one year. That exact definition, a carbonyl group bonded to two carbons. So you need to be very careful. The double bond O bonded to the carbon, that is your carbonyl group. I often thought that the carbonyl group was the entire picture. But no, the carbonyl group is your double bond O and the carbon it is attached to. Right, the last two, carboxylic acids and esters. Carboxylic acids is like a little bit of a combination of an aldehyde and an alcohol. You know, we have our double bond oxygen on a primary carbon, and on that same carbon we have an OH group, where the OH is just referred to as the hydroxyl group, and the double bond O on a carbon is often referred to as the carbonyl group. We now combine those two names, and if we have a double bond O on a carbon that is also bonded to a hydroxyl group, that entire group is called the carboxyl group. I hope that you can now go and see why things are named the way they are. And lastly, we have esters. Now, guys, esters you should be very familiar with. It was a compulsory practical, and if you did your esters practical in term 1, you would have had the most amazing smells in that laboratory. So an ester is an alcohol and a carboxylic acid bonded to each other. And in just a little bit, I'll explain to you how to name esters from their alcohol and their carboxylic acid, as well as what to look out for. Because that's the thing I always struggled with. Like, which part comes from the alcohol and which part comes from the carboxylic acid? Don't worry, guys. I'll help you figure it out. Easy peasy. Right. The next thing that you have to be able to do is to differentiate between saturated and unsaturated compounds. Guys, they do ask this. I've seen it year after year after year. A saturated compound is where there are no multiple bonds between carbon atoms in the hydrocarbon chain. You need to be very careful. If there is a double bond oxygen on a carbon, that is not seen as unsaturated. Saturated compounds, we very specifically look at the bonds between carbon atoms within our hydrocarbon chain. And this is pulled through to our unsaturated compound definition. So we have for unsaturated compounds, a compound with one or more multiple bonds between carbon atoms in our hydrocarbon chain. Please make sure that you understand the difference between a multiple bond between carbon atoms and a multiple bond between an oxygen and a carbon atom. Right, now, sure, the fun stuff. Guys, you have to be able to draw 3 different types of formulas. The first one is your structural formula, and this is a chemical formula that shows you what atoms you have within your molecule. It shows all the bonds between the atoms. It shows whether the bond is singular, double or triple, and it gives you a very good indication of what the molecule could look like in 3 dimensions. This must be my favorite formula. It clearly shows you everything. I have to admit it's my least favorite to draw because I have to add in all the hydrogens. But when I am faced with formulas, I very much prefer to have a structural formula because it shows me the big picture. Now, we also have molecular formulas. Now, guys, you've been dealing with molecular formulas since grade 10, possibly before that, okay? A molecular formula is a chemical formula, and it shows you the type of atoms and the number of atoms in each molecule, right? Today, we're not going to go into too much detail about the difference between a molecular formula and an empirical formula. That you would have to go and re-look your grade 10 and 11 notes for. Then in organic chemistry, we also have a combination between structural formulas and molecular formulas. And these are called condensed structural formulas. So you start with the basic idea of a structural formula, but you don't show all the bond lines. They often like to group together functional groups or methyl groups or ethyl groups. So a condensed structural formula gives you the picture that a structural formula would give you, but is shorthand and uses molecular formula when needed. Right, now, I'm pretty sure that this table, by now, you guys are all very comfortable with. Guys, you have to know these names. For me, the first 4 are a bit iffy. I had to really go and learn them. But the last 4 are very simple because they come straight from mathematics. Pent, hex, hept, and oct. So if you know your first 4, then naming your carbon chains are easy. right? So for 1 carbon in our longest chain, we have meth. For 2 carbon in our longest chain, we refer to it as an eth. For 3 prop, 4 bute, 5 pent, 6 hex, 7 hept, and 8 oct. Now you are only going to be able to successfully name your compounds if you can combine the naming for each of the number of carbons with the name for each functional group or each homologous series. So let's look at what we would add to each of these parent names to show what type of organic molecule we have. I've ordered these in the same way as the exam guidelines orders their diagrams. So we start with alkanes. If we only see single bonds between carbons and we only have carbons and hydrogens, we add ANE, ane, to the end. For alkenes, enes, and for alkynes, ines. Those make perfect sense to me because they are the end of those homologous series names anyway. Alcohol, same story. An alcohol ends in -ol. Now, aldehydes are a bit weird. Aldehydes, instead of using the end of the name, we use the beginning. So for aldehydes, names end in -l. Ketones, again, follow the old recipe. We add the end of the homologous series name in -one. And carboxylic acids is oic acid. Now, esters we are going to deal with in a little bit. But the alcohol you use, say for example you had methanol, then you would have methyl. So that whatever alcohol you use gets the methyl group in, and for whatever carboxylic acid you use, you add O8. So if we had methanol and ethanoic acid, the ester formed would be methyl ethanoate. Don't worry, it takes a lot of practice to get the names for esters right. We will look at it again in just a little bit. Now we have one more thing that we have to add when we name. We have to add our substituents. Now substituents is a very big fancy word for added extras. In grade 12, they can ask you to name a methyl group, so an added extra group with only 1 carbon, or they can ask you to add an ethyl group, so an added extra group that's not part of the longest chain that contains 2 carbons. They could also ask you to name any of the halogens. Now, chloro, bromo, and fluoro, we tend to see a lot. Iodine we don't, and iodine we refer to as iodo. I really enjoy that name. Now, not only with substituents do we have to tell the examiner what substituent it is, we also have to tell the examiner how many. If there's only 1, we don't have to say anything about it. But the second we have 2, 3, or more, we have to tell the examiner that by putting a prefix in front of the name of the substituent. In grade 12, you will only be expected to deal with 2, 3, and 4 of the same substituent. So if there are 2 methyl groups, when we name it dimethyl. If there are 3 methyl groups, when we name it, we name them trimethyl. And when we have 4, we refer to it as tetra. Right, guys? I hope that this, revision, stuff that you should have done at school already, things that you have definitely seen. This is just a reviser, refresher course. Now, very important, guys. You need to be able to draw a molecule from its name, and you need to be able to name a molecule from a drawing. So let's just pause here for a second. Let's just think. What do you find harder? For me personally, I find it much easier to name a molecule if I've been given a drawing. Some people, and many learners I know, find it easier other way around. They prefer to have a name and then draw the molecule that they see. However, you need to be able to do both. So what I'm going to do is I'm going to give you a very brief summary of the process that I follow in order to either draw the molecule from a given name, or if I have a molecule and I'm asked to give the IUPAC name, to give that name. Now guys, this is not hard and fast. Some of you will prefer to do it in a slightly different order. Ultimately, that decision is up to you. All I would like to do today is to share with you my method, my way of doing it, so that you can see if maybe this helps you. Now, I know often, especially if you ask for a name from a drawing, all the lines, the carbons, the hydrogens, all of it becomes very overwhelming, which is why I want to give you a step-by-step instruction just to make your life a little bit easier. So let's see how I would approach the two slightly differently. Let's first look at when I draw a molecule from a name. So when I draw a molecule, the first thing I do is I draw the longest carbon chain. So if, for example, I'm given pentane, then I go and I draw my 5 carbons. Once I've drawn my 5 carbons, then I add the functional group. Now, this is why I only add my bonds after I've drawn the right number of carbons. So whether you have pentane, so you're only drawing single bonds, or whether you have a pentanol, so you have to go and add an OH group, that you have to then deal with at this point. Now, the reason I say that you deal with the functional groups and then the rest is very important. Once you've added your functional group, so that's the N part of the name, you need to add your substituents, the beginning part of your name. So carefully go look on which carbon does which substituent need to go. Now notice I haven't started drawing in my hydrogens. I always leave those for right at the end. Now this seems like a very weird step, but guys, I promise you this saves you time and it saves you mistakes. Once you've drawn your carbons and you've added your functional group and your other substituents, I want you to go and look at every single carbon you've drawn and count to 4. Every single carbon you draw must have 4 bonds, whether that's a double bond, which then counts for 2, or just single bonds. Make sure that at every carbon you count to 4. And as I count to 4, the lines that or the numbers that I'm missing, I draw a line for. Because then I know that these lines, these empty lines, they need the hydrogens. So I draw my hydrogens right at the end after I've figured out my longest carbon chain, I've added my functional groups, I've added my substituents, and I've made sure that every single carbon has 4 bonds attached to it. Now, if you have to name a molecule from a drawing, I follow a very similar system with slight differences because now I don't need to count to 4 because I'm hoping the examiner can, and I don't need to draw in my hydrogens. So, when I name a molecule, the first thing I do is I go find the longest carbon chain. Very important. 1, it has to contain the functional group. And 2, it's not always in a straight line. Guys, when you get a molecule, please do me the favor. make sure that you double, triple check that you have counted the longest carbon chain and not just the straightest carbon chain. Okay. The next thing I do is I identify the functional group. Now I know this sounds like I've done this in one first. I haven't quite. You find the longest carbon chain in number 1, making sure that it includes a functional group. And now in number 2, you identify that functional group so that you can give the name of your molecule its suffix. Now we have to figure out the numbers. Before we figure out the numbers, we have to know where are all the other added extras. So once you've identified your longest carbon chain and you have your functional group, it's often useful at this point to use color. So in color, you write the carbons that are part of your longest group. In a different color, you identify your functional group, and then yet another color, you identify all the added extras, everything that is not part of that longest chain or that is the functional group. And now we have to count. And guys, I often see lots of mistakes with this. Remember, when we count, we want to have our functional group on the lowest possible number. Then we want our substituents on the lowest possible numbers, preferably in alphabetical order. If you're not sure whether you counted from the right direction, a handy hint you can use is to add all the numbers up that you have got in your name. If you have 2 possible options and you're not quite sure which way to go, it's often useful to add the numbers up and see which of those two sums give you the lowest possible number. The lowest possible number will be the most correct naming. I hope that helps a little bit, because I know often students find this part of the work very, very hard. And actually, guys, this is good, easy marks. Right. Now this brings us to our next part of organic chemistry. We've now dealt with the basics. We've dealt with all the different functional groups. We have dealt with naming. Now we need to start dealing with, that looks similar to something else. What do I do with it? So, the first definition in this section you need to have a handle on is structural isomers. Now, structural isomers are organic molecules with the same molecular formula, but different structural formulas. Now, I'm going to say something quite scary. In your grade 12 paper, all isomers can be classified as structural isomers. And then, from there, we classify them further. Now, guys, this is a very big sweeping statement, and I don't want you to think that it is always true. But remember, when we started, I said I was going to give you a couple of handy hints, things to help you answer your paper with more confidence. So we need to be very, very clear on how all of these definitions fit in together. When we're dealing with isomers, the broad topic is structural isomers. So we have 2 molecules that have the same molecular formula, but they don't quite look the same. From there, we have to decide, is it a chain isomer, a position isomer, or a functional isomer? And now I know my students really, really struggle with the difference between chain isomer and positional isomer. So I'm going to give you a few mnemonics to just help you out just a little bit with those. Let's have a look. So the first one we're going to deal with is chain isomers. So chain isomers have the same molecular formula but different types of chains. And my students always say to me, "Ma'am, what does that mean?" Now, the simple, easy way is to remember that a chain isomer, I move a carbon. So the C's go together. So basically, a chain isomer is when I take a part of the carbon chain, I chop it off, and I put it somewhere else. So chain isomers, I move a carbon. And this is where chain isomers and positional isomers are close, but not quite the same thing. Positional isomer has got the same molecular formula, but substituents or functional groups are on a different position. So guys, handy hint here, when you want a positional isomer, you can move the position of anything other than a carbon. If you move a carbon, you are creating a chain isomer. I hope that sorts out that little difficulty. And then our third type are the easy ones. It's functional isomers. Now this is very, very easy. A functional isomer has different functional groups. Now you need to be very careful. There are two sets of functional isomers. The first set is esters and carboxylic acids. Esters and carboxylic acids can comfortably have the same molecular formula, but different functional groups. And now we get to the one that lots of people forget about. Ketones and aldehydes. Now guys, I know this feels very weird because a ketone has got a double bond oxygen and an aldehyde has a double bond oxygen. But you need to remember back to the basic definition of homologous series and functional groups. Okay? The reason why they have distinctly different names and their functional groups have different names is because they have distinctly different chemical and physical properties. Although we can see similarities, that difference between being on a primary carbon or being somewhere in the middle on a secondary carbon makes a huge difference. And that is why ketones and aldehydes are also seen as functional isomers. Be careful for that one. They do like to ask it, and they like to ask it because it's an easy catch out. So just keep your eyes open for that one. Right, now we get to our ever famous question 3, physical properties. Now guys, I know that you have done melting and boiling points since grade 10. But I also know that you guys like to say that the melting point is the point at which a solid and a liquid phase of a substance is in equilibrium. Please, please, please make a point of writing temperature for yourself in your notes in big capital letters, in red if you have to, and highlight it. That is such an important little word, and I see so many students at the end of the year exam, when you are under pressure, forget that it's not the point at which a solid and a liquid phase is in equilibrium, but the temperature at which solid and liquid phases of a substance are in equilibrium. Now, boiling point has got the same catch. It is the temperature. And now, guys, you need to remember that this is the only definition of boiling point that is acceptable. Melting point is where a solid and a liquid is in equilibrium. Boiling point, you cannot say that it is where the gas and the liquid phase of a substance is in equilibrium. That definition is not accepted in the final exam. So first problem for boiling point is you have to say it's a temperature. And then the second part, you have to tell them it's where the vapor pressure of a liquid equals atmospheric pressure. Now that brings me to the definition of vapor pressure. Guys, again, these definitions I pulled exactly from your exam guidelines. They are all in there. Vapor pressure is the pressure exerted by a vapor at equilibrium with its liquid in a closed system. Now I'll show it to you in the post-test. They can ask graphs in this question, and they often do. In this question, they can give you a table, and the table could have either the melting points or the vapor pressures in, or they could give you graphs, and the graphs could have either the boiling points or the vapor pressures. And this is why it is so important that you don't just rote learn your definitions, but truly understand how to apply them. And of course, if we're talking about boiling point and vapor pressure, we have to talk about intermolecular forces. Guys, intermolecular forces definition is not asked often. However, don't be lax about it, because this definition is in the grade 12 guidelines. It is important that you also know it. The trick word here is the force of attraction. I sometimes see people just say it's the force between molecules of a substance. But remember, it could be the force of repulsion as well. So that word attraction, that's an important word. Now we're going to look at how intermolecular forces affect boiling point and vapor pressure. So, I have summarized the different types of intermolecular forces that you need to be familiar with for organic chemistry. I don't want you to think that this is a comprehensive list of all intermolecular forces. I have focused in on the intermolecular forces needed in the question paper specifically related to organic chemistry. So the first type that you have to be aware of is van der Waals forces. Now, van der Waals forces we will see between non-polar molecules. So your alkanes, your alkenes, those type of molecules. Then we get dipole forces. And dipole forces is when you have a polar molecule, often caused by that double bond oxygen, to a carbon. Now you need to be careful. When I phrase this, I had to really look at the definition, and I had to really puzzle it out in my head. And I will show you with the next definition where the difference lies. So our third type of intermolecular force that we need to be well versed with is hydrogen bonding. And hydrogen bonding is the force between a hydrogen and an oxygen atom. Right. So now you'll see that there are almost similarities between the dipole forces and hydrogen bonding. So let's just talk about them for a second, okay? When we have an organic molecule and it has a double bond oxygen to a carbon, although there is an electron negativity difference between the oxygen and the carbon, it is not hugely significant. And therefore, that area is a dipole. It is polar, but we don't have hydrogen bonding. Why do we not have hydrogen bonding in an area where the oxygen is double bonded to the carbon? Well, that's very simple, because there's no hydrogen bonded to the oxygen. Guys, you need to be very careful of this definition. Hydrogen bonding can only occur when I have a hydrogen that is bonded to a highly electron negative atom, such as oxygen, fluorine, those guys. Okay, so when we look at organic molecules, we have to make sure that our hydrogen is bonded directly to the oxygen and not to a carbon that is also bonded to an oxygen. Please watch out for that little catch point and make sure that you make your notes really carefully and explain the difference to yourself. The reason I'm saying this is dipole forces are much weaker than hydrogen forces. And so you have to be able to compare the two in that way. So lastly, for this question, you need to know the aspects that affect intermolecular forces in organic chemistry. Now, the first and logical one is the strength of the intermolecular force. And then we get to the type and the number of the functional groups. Then, very important and often quite hard to explain is chain length and molecular mass. And the last aspect is how branched a chain is. So guys, these are the 4 aspects you need to be able to describe and argue in a chemistry paper when confronted with different boiling points or different vapor pressures of different molecules. Right. Now, just before we get to the general chemistry equations, let's look at estification. Now first, before we start, let's just look what they say in your exam guidelines about estification. So under estification, they say you have to be able to write down the equation using structural formulae for the formation of an ester. You further need to be able to name the alcohol as well as the carboxylic acid, as well as the ester formed. And you need to be able to write down reaction conditions for estification. A couple of years ago, they asked in the national paper in November, the first organic question was an estification question. And I remember they went into so much detail and lots of people missed little words. So I just want to put some emphasis on a few aspects if they decide to ask you quite serious questions about estification again. So firstly, your reaction conditions. You need concentrated sulfuric acid, so H2SO4 concentrated, as a catalyst. Then when we get to naming, the first part of the name comes from the alcohol. The second part of the name comes from the carboxylic acid. And now often my students say, but ma'am, how do I know which part comes from the alcohol and which part comes from the carboxylic acid? Now, it's very, very simple. And I know it sounds when you say it this way, it's like, oh, of course. Your carboxylic acid starts with a double bond oxygen as well as the OH group. The OH group gets removed, but that double bond oxygen remains on that carbon. So when you're busy with an ester, you find your oxygen in the middle of all the carbons, and then you go look which side of that oxygen has the double bond carbon on it. You find that double bond carbon, and that is the side of the ester that comes from the carboxylic acid, and therefore the other side comes from the alcohol. So guys, just remember that when you've got an ester, go find the oxygen in the middle of the carbon chain, then go look which side of that oxygen is my double bond O on my carbon, and that's my carboxylic side. Easy peasy, nah? Now, when you do this experiment, your teachers will drill into you that alcohols and carboxylic acids are flammable. And a few years ago, they asked, why should the contents of a test tube be heated in a water bath and not directly over a flame? And lots of people struggled with this answer. So I want to just make it sure that you understand that the contents of the test tube is flammable. The test tube itself is not flammable. It's going to get very hot, and if you touch it with your fingers, you'll probably have some proper blisters. But the test tube is not flammable. You have to be very careful with your wording here and make sure you tell them that the contents of that test tube is flammable. The last little part of organic chemistry with estification is this drawing. I just want to make sure that you understand which part from which formula gives us the ester. So from the acid, the entire OH gets removed, and from the alcohol, the H bonded to the O gets removed. Then with our ester, we get our carbon with an oxygen in the middle. The carbon with a double bond oxygen comes from the carboxylic acid, and the other side of the chain comes from the alcohol. And then guys, I see this time and time and time again. Do not forget to add the water. Most of my students always remember the acid and always remember the alcohol, and 99% they get the ester right, but about 50% of them forget to draw the water. If you are asked for structural formulas, it's safer to draw water, similar to like in this diagram, but you could also get away with going H2O. Just be careful of how they ask the question. Right, so last little bit of organic chemistry is definitely all the reactions. Now guys, don't panic. I know this looks busy. I want you to start with the key on the right bottom side of your screen. What I did is all the reactions I ordered either by substitution or addition or elimination. And then I realized, but hang on a second, we actually have two reactions in the curriculum that doesn't quite fall under substitution or addition or elimination. That is esterification and that is combustion. So I added those two in different colors. So please don't panic about this diagram, okay? If you know your reactions well, this diagram will make a lot of sense to you. Because if we go from, say, for example, an alkene to an alcohol, we add water, so we hydrate. If we go from an alcohol to an alkene, we dehydrate. So you'll see that often two arrows, a green and a red, will go together. A green will be the addition reaction, and the red will be the elimination reaction. Right? And then we have our three substitution reactions. Now, the only specific name you have to remember for substitution is when you go from an haloalkane to an alcohol, and that is the process of hydrolysis. Right. Then, guys, it is very important that you know all your reaction conditions. And so here I have summarized them for you by type of reaction. So I've started with the addition reactions, given you those four, and given you the exact conditions for each of those. Then for elimination reactions, you need to double check as well. Remember guys, some of them have strong concentrated base, some of them have strong concentrated acid. And please remember that there is a difference between a strong concentrated acid and a weak concentrated acid, or a strong dilute acid and a weak concentrated acid. You need to be very, very careful that you have exactly the right wording. This is why I put the formulas of suggested catalysts down for you so that you can see which block they fall into. Right guys, so that brings us to the end of organic revision. I hope your brain is not completely exploding. You might want to pause the video at this point in time, stretch your legs a little bit, get your brain ready for physics, because the next 3 sections we're going to do is going to be on physics. Now, before we start with them, I want to remind you that Newton's laws come from grade 11. You did all Newton's laws in grade 11, all 4 of them. I think you guys often forget about the universal law of gravitation. But they are required for grade 12. And what is more, they are often question 2 in your grade 12 physics paper. It is well worth your time to go and revise the definitions, Make sure you know them off by heart, quicks. You shouldn't even really have to think about them. And then be very, very sure that you can actively use them. Right, so what I've done is I have given you the revision of Newton's laws. Everything you should know from grade 11. And I've given you a couple of hints and tricks and tips on how to apply them. So let's just gently work through these. So, guys, Newton's first law tells us that a body will not move unless a non-zero net force acts on it. You'll notice that I always refer to non-zero and net forces. If you look in the exam guidelines, there are alternative words for them. The reason I refer to specifically non-zero and specifically net force is simply because of how the definitions ends up translating into formulas. Now guys, I didn't put the formulas down today for you. You need to remember that most of your formulas are on the information page. Get an information page, print it out, stick it in the front of your book. Always have it with you so that you know exactly which formulas you get and which you don't get. So Newton 1, body will remain at a state of rest or constant motion, so constant velocity, unless a non-zero net force acts on it. The second law tells us what happens when we now have a non-zero net force. Guys, this one's got lots of tricky spots in it. Newton's second law says when a non-zero net force acts on an object, the object will accelerate in the direction of the force. Lots of my students tend to forget in the direction of the force. They just say the object will accelerate. In the direction of the force is an important part of this definition. That gives you your first mark. Your second mark for this definition comes from the second sentence. The acceleration is directly proportional to the magnitude of the force and inversely proportional to the mass of the object. Guys, remember the word inverse means 1 divide by. And if you really struggle with this definition, remember that the entire second part of this definition you can get from Newton's second law equation. And now poor Newton's third law, often forgotten. When object A exerts a force on object B will exert a force on object A. These forces will be equal in magnitude but opposite in direction. Now, please don't write the bottom sentence. I simply always put it there to remind you guys in short what Newton's third law says. Newton's third law in much shorter terms says every action has an equal but opposite reaction. Please do not write that as part of your definition. That is not the definition required by the exam guidelines. And then the poor forgotten fourth law, Newton's universal law of gravitation. Guys, please go and do yourself a favor and go and learn this one. They do ask it every now and again. And I personally think because you get the equation for this law, this is one of the easiest definitions to get. Everybody attracts every other body in the universe, but that force is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. That word product and that word square, often forgotten. Guys, go look at the formula. It's mass 1 times mass 2. And it's divided by the square of R. Please do yourself a favor and make sure that you can go and look at those formulas and gather a definition from it. Now for this question, there are some other definitions that you also need to know. the definition for normal force. Very, very important about normal force, guys. It is always perpendicular to the surface, no matter which direction that surface points. Then we have frictional force, and frictional force is always parallel to the surface. I sometimes see students draw weird arrows at weird directions. In just a second, I'll give you a couple of handy hints on how to draw free body diagrams. And then the last one is weight. Now, again, guys, I know we more often than not deal with parallel and perpendicular weight. That is fine. But please remember that the definition of weight means it is always straight down to the center of the earth. Right, so let's talk about free body diagrams. When you draw a free body diagram, you start with a dot. Now, this is not part of the mark you will receive, but let me explain to you why I strongly recommend that you draw the plane in with a pencil. So, we've already said that the normal force has to be perpendicular 90 degrees to the surface, and that friction must be parallel to the surface. So often I see people and they kind of get their normal force 90 degrees to where they think the plane will be, and then they don't quite draw their frictional force on that same plane. And you could lose marks for that. So what I strongly recommend is that after you've drawn your dot, you take a ruler and a pencil and you draw your plane in. This is obviously less important if it's a horizontal plane, but if it's an inclined plane, it greatly helps. You draw your incline in, and then it is easy to draw frictional force and normal force and still keep your weight straight down to the center of the earth. I hope that makes a little bit more sense. So then we are going to draw all the forces, and the arrows are going to point away from the dot. Guys, again, one of those things that I cannot tell you enough. When you draw a force, even if it is a pushing force, the arrow has to point away from the dot, representing the object the forces are acting on. And now, something that I tell my students often, and that I sometimes think they forget. If you are asked for a free body diagram and the question counts 4 marks, guys, I can guarantee you need to draw 4 forces. Now, please be careful that 2 components of a force do not count as 2 forces. This is especially important if you have applied forces at an angle, or if you are working on an inclined plane and you have to work with parallel and perpendicular components of weight. Now, if I teach you nothing else today, I hope that you will take this away with you. Once you've drawn a free body diagram as a question requires, I want you to redraw that diagram and split all the forces into parallel and perpendicular components. Why is this important? If you have an applied force that is pushing down on the object, then your normal force increases. If you have an applied force pulling up on an object, your normal force decreases. But if you do not split your forces into perpendicular and parallel, you will miss those. Every single year for the last few years, they have asked questions to that point. They have asked questions where either the tension or the applied force influences the normal force. So I really, guys, I cannot encourage you enough. Please split your forces and split them into parallel and perpendicular. These make your calculations so much easier. Now, there's a couple of ways that they can ask you questions. And if you tell me, but ma'am, I didn't know this, I'm going to point you straight back to your exam guidelines. Everything that I pulled out from this is straight from the exam guidelines. So, they could ask single body, so one body. They could put it on a flat horizontal plane, and they can ask it with or without friction. They can also put a single body on an inclined plane, and again, with or without friction. And the last type of single body question they can ask is vertical planes. Now, in this situation, you'll be dealing with a lift or a rocket, something that goes up and down. I don't want you to confuse this with the section of vertical projectile motion, but be aware that they could ask in question 2, when they're working with Newton's laws, they can ask you vertical up and down questions. Now, this is the more common type of questions, two-body questions. Now, it will always be joined by a light, inaccessible string. This means that the tension in that string will always be a constant. And again, guys, remember, tension does not have a direction. Tension has a direction when acting on an object. So if a string joins object A and B, and we're pulling object A, then the tension in the string pulls against object A, but it pulls object B forward. The magnitude of the tension in that rope will be the same, but the direction depends on the object it is acting on. So if you are ever asked to calculate tension, please do me a favor and don't add direction. Magnitude only. So, for two body diagrams, we could either have both on a flat horizontal plane, and again, the plane could be with or without friction, and we could have an applied force either parallel to the plane or at an angle. Both objects could be on an inclined plane, again, with or without friction, and the applied force could either be parallel to the plane or it could be at an angle to the plane. Now, this is one we've seen a couple of times. You have one object on a horizontal plane. That horizontal plane could be with or without friction, and the second object is hanging vertically down from a string. However, it is very clearly stated that the string has to be over a frictionless pulley. And guys, they will not ask you an inclined plane with a second object hanging vertically down. If you read through your exam guidelines, it is not stated as a possible question that you have to deal with. Now, this is one we haven't seen for a couple of years. Both objects hanging vertically down from a string over a frictionless pulley. This is quite an interesting one. I really enjoy working with questions like this. So guys, that is how they can ask you the questions. Now, what do I look out for? I'm going to say this again. Make sure you split every single one of the forces that you are dealing with into a parallel and a perpendicular component. Watch out for forces that pull up or push down on an object that influences the normal force. Which brings me to my third bullet. Do not assume that the normal force equals the weight, but just in a different direction. So guys, on that point, I want to encourage you, whenever you are calculating normal force, please look at all the forces acting perpendicular to the surface and make sure that all the forces add up to 0. it is unlikely that an object will be floating away into space. And so that is where you use your Newton's first law and say F net equals 0. This gives you a better chance of calculating the correct normal force. Why is this important? Normal force is used to calculate friction. So if you have the incorrect normal force, you are going to calculate the incorrect frictional force. Now I know, I mark papers too, we mark with your mistakes. But if it's in the same question, we cannot do that. So I really strongly want to encourage you, please, when you are calculating normal force, don't be lazy. Make sure that you have all the forces on the perpendicular to the surface plane. Add all of them together. Remember, pick a direction as positive and the other one is negative, and get 0. This means that your compounded incorrect calculations become so much less. Right, guys, so that brings us to the end of Newton's laws. We only have 2 more to go. If you need to pause the video at this point in time, please be my guest. Don't worry about it. I know this gets like a really, really long session. All right, but next up, we're going to look at momentum. We've only got momentum and vertical projectile left. They are not ridiculously long. The questions asked in these 2 questions are also not very tough. So, momentum. Oh, this formula. Guys, you get this formula. P equals mv. And that is the definition of momentum. It's the product of an object's weight and its velocity. Again, don't be caught out just because it's such an easy definition. Make sure that you know it. Now, this is one we don't often see asked as a definition, but it is one we often use in calculations. This is Newton's second law in terms of momentum. The net force acting on an object is equal to the rate of change of momentum of the object in the direction of the net force. And this definition brought us to impulse. Now, again, guys, this is one of those that I see lots of people struggle with. Impulse is the product of the net force acting on an object and the time the net force acts on the object. And impulse is equal to the change in momentum. Now, the last big definition is the principle of conservation of linear momentum. Now, this definition I see so many people trip over. So, the important word here is the total momentum. You could get away with not writing the word linear momentum in your definition, but you are not going to be penalized if you do. You will, however, be penalized if you do not have the word total in your definition. So the principle of conservation of linear momentum, the total momentum of a closed system remains constant. Guys, it's an easy one. They like to ask it. Make sure you know it. Then we have 2 more concepts that we have to deal with in terms of momentum, and that is the idea of elastic collisions and inelastic collisions. Now, first of all, guys, when you have to calculate elastic and inelastic collisions, make sure that you have a closed system so that you have conservation of linear momentum first. Then you can go and calculate elastic or inelastic collisions. So an elastic collision is where the total kinetic energy of the objects within an isolated system remains the same. They stay constant. They are conserved. Therefore, an inelastic collision is one where the total kinetic energy of the objects in an isolated system is not conserved. Guys, those are 2 of very, very, very easy definitions. Now, I want to just draw your attention. If there is a collision, one car bumping into another, often the kinetic energy before the collision will be greater than the total kinetic energy after. Why does this happen? Because some of the energy is taken away from kinetic energy and transferred into heat or sound or deformation. There's a whole bunch of different things. So when you have a collision, two cars driving into each other, you will often find that the kinetic energy before is bigger than the kinetic energy after, because energy is lost, if I can say in inverted commas. I don't like the word. Energy is transferred, is what I prefer. Now, if you take the opposite, if you look at explosions, often the total kinetic energy before an explosion will be much smaller than the total kinetic energy after. Why does this happen? Whatever triggers the explosion, so let's say, for example, a spring between two trolleys, this explosion transfers energy from the object that causes the explosion, the spring, and it takes that stored energy and transfers it to the objects that are being pushed apart. This is something that I find very interesting, and if you have some time, go do a couple of calculations and see if you find the same thing I do. Right, guys, that wasn't so bad. So that is the end of momentum. We've only got one topic left. We only have vertical projectile motion. Now, vertical projectile motion has got quite a lot in it, okay? I'm going to run you through the basics, and I'm going to very briefly give you an idea of how to do calculations using graphs. I'm not going to go into a lot of detail, but I just want to give you guys an idea of where to start when you're really struggling with a graph. Right, so let's have a look. Revision of vertical projectile. Now, the first thing that is important, you need to know the definition of a projectile. It is the object upon which only the force is gravity. And this object is said to be in free fall. Now, guys, I'm going to run you through a couple of important concepts with regards to vertical projectile motion. So the first one, and I'm sure your teachers have drilled this into you too, when an object is in free fall, the acceleration of the object is always 9.8 meters per second squared down. And guys, they like to ask this as a question. It's important. And luckily you do not have to remember this value because it's on your information page. It's in the table. The name of the value is the acceleration due to gravity, symbol little g, and the value is given there as 9.8 meters per second squared. Right, equations of motion. These equations of motion you learned for the first time in grade 10. You use them again for vertical projectile motion, and often in your exam information page, you will find that you also have the option to use delta y. Delta y referring to the fact that it's going up and down rather than left and right. Guys, you do not need to memorize these equations of motion. They are on the information page. What I do want to encourage you, when you use them, make sure you write them down exactly as they appear on the information page. And please make sure that you include all squares. I see this quite regularly. People will get a time of 2 and then forget to square the 2. They'll do it on their calculator, but if you don't write it down in the substitution, we cannot give you that substitution mark. It pays to be very precise. Just quickly, these symbols, delta x is displacement or change in position, and that always has to be in meters. VI is our initial velocity in meters per second. VF is our final velocity in meters per second. A, acceleration in meters per second squared. And delta T is time taken in seconds. Please make sure that you write down your units as you write down your variables. And I want you to convert them as soon as possible. Don't wait until you forget to do it, substitute the wrong value into your equation, and then get a very wrong answer. I also want to encourage you to always choose a direction as positive, either up or down, or left or right. So please, guys, when you are working with Newton's laws, forces, or you are working with vertical projectile motion, even when you are working with Doppler and with work energy theorem, all of these, you need to make sure you choose a direction as positive and that you stick with that positive direction. And lastly, when we're working with vertical projectile motion, instead of using A, we tend to use G. We tend to use G because that is the acceleration caused by the gravitational pull of the Earth. And it is 9,8 meters per second squared down. And the last little thing I want to remind you of, if no one's told this to you before, the velocity at the maximum height of any vertical projectile motion is 0 meters per second. It's the point when the object has just stopped moving up and now starts moving down. Right, guys, we are almost there. Time symmetry is a statement and a concept that I don't think gets enough attention. Time symmetry says that the projectile takes the same amount of time to reach its highest height as it takes to fall back down to the point where it was launched from. Now, this is all good and well, but guess what? This means more than just this. So firstly, I can say, well, the time taken from start to maximum height equals the time from maximum height down to the same point. But it also means that the speed with which I send the object upwards is the same speed that the object will have at that same height, but going down. Right. So guys, that is the theory part of vertical projectile motion. You know we get graphs, sure. And I know when we deal with graphs, there's lots of headaches. So, this is what a position time graph looks like when we're dealing with vertical projectile motion. It has a curve. It shows you that the upwards velocity starts at a bigger magnitude, slows down, for a second is 0, and then the velocity, the magnitude increases, but coming down. And this shape is echoed by our velocity time graph. So for the same movement, a velocity time graph would look something like this. You'll notice that for this example, I chose up as positive. So because my object is traveling upwards, I start with a positive velocity. The higher this object travels up, the slower it does so. Its magnitude of velocity or its speed gets slower until it reaches its maximum height. For this object, that happens at 1,5 seconds. The object then turns around and falls downwards. Now guys, the acceleration time graph for vertical projectile motion is exceptionally boring. It's a straight line. We can do some calculations with it, but this graph is not often given. But I don't want you to disregard it. There's one more type of graph we quickly have to look at before we do some calculations, and that is bouncing balls. So this is the position versus time graph for a bouncing ball. It looks similar to the position versus time graph of a simple projectile motion, but as it hits the ground, it then gets projected upwards. And you'll notice that the bounce at each projection is slightly less than the previous one. The comparative velocity time graph would look something like that. We'd like to see that the gradients of each of the velocity lines is the same. And we can do several calculations with this. So, guys, I'm going to switch you guys over to my trusty whiteboard where I have lined up for you a position time, a velocity time, and an acceleration time. And I'm very, very briefly going to show you how you deal with any calculations that you might have to do from the graph. Okay? I will take you back to the PowerPoint and I'll just give you the summary of these. Okay? So don't panic. But just to give you an idea of what we could be asked to do other than just read a value from the graph. So let's have a look. Right. So the first thing we could do from this position versus time graph is be asked to calculate a velocity at a specific point. Now, this is not the easiest thing in the world to do, especially when you are not able to differentiate at a point. But let's try and just have a look at how we could do this. So guys, if we need to get a velocity from a position time graph, we need to calculate the gradient. So I've taken my ruler and I've drawn with my ruler a straight line, a tangent at the position where it is 0,5 seconds. This is just rough. Right, so there's that line. Now we can use this tangent line that I drew and roughly estimate what the velocity at 0,5 would be. So, to calculate a velocity, we need to have a y1 and x1 and y2 and x2. So I am going to just take this line and extend it down, and I'm going to pick 2 points, one either side of 0,5. That one looks like it's pretty close to a line. Again, guys, this is going to be a very rough estimate of the gradient of this line. Now I'm going to find the corresponding y values. This is, of course, much, much easier if you have a straight line graph. So that is going to be our y1 And that is going to be our y2. Right, so let's pack the ruler away. Let's look what we're dealing with. So I'm going to call this x1. Its corresponding value at y is going to be y1. And if I look at this graph, each of these lines represents 2 meters. So this line here is going to be 4 meters. Then for x2, which is at 0.9 seconds, I'm going to follow it all the way up. And this is going to be y2. Now again, each of these lines represent 2 meters. So 2, 4, 6, 8. Let's estimate that at roughly about 10 meters. Okay, I want gradient. The gradient gives me the instantaneous velocity. Gradient is rise over the run. It is the change in y over the change in x. Don't swap this around, guys. That's why I say it is the rise over the run. So I'm going to go y2 minus y1 over x2 minus x1. Please make sure that if y2 is first, x2 has to be first. And if y1 is second, then x1 has to be second. I'm going to substitute these values in. And I'm going to get 10 minus 4 over 0.9 minus 0.3. Oh, that's a lucky value. That's 6 over 0.6. And if my math is not too bad today, that means that the instantaneous velocity at 0.5 seconds, because remember, that's where I drew the tangent line. I drew the tangent line to the curve across from 0.5 seconds. So that means that the instantaneous velocity at 0.5 seconds is 10 meters. Let's have a look how close I was. Oh, not too bad, 9.8. I'll live with that. Now, guys, a velocity time graph we can do 2 things with. The first and way too easy thing to do with a velocity versus time graph is to calculate the gradient. The gradient gives us the acceleration. And what do we know about acceleration and vertical projectile motion? It is always 9.8 meters per second squared down. I chose up as positive for this entire graph section. So for this one, I can guarantee you it's going to be 9.8 meters per second squared. Negative. Now the calculation I want to show you is calculating the area under a graph. So if I have velocity versus time and I calculate the area, then I get the displacement. Right? That makes quite a lot of sense because when I calculate the gradient from displacement, I get velocity. So if I want to go backwards, I have to do the opposite. I have to get the area. Now, guys, if we look here, let's use similar values to what we used earlier. Let's say I want to calculate the displacement for this object between 0.2 seconds and let's say 0.5 seconds, shall we? So I need to calculate the area under the graph between 0.2 and 0.5 seconds. Now you'll notice that that is quite a funny shape. That's okay. We can take that funny shape and we can split it into a triangle and into a rectangle. Guys, none of this information is on your information page. This is content knowledge, and these are things you need to go and practice. All right, so now we've got here a rectangle and a square. The rectangle area we are going to get by saying base times height, and the triangle is going to be half times base times height. Now be careful, it's not going to be quite the same base and same height. I'm going to use this here as my base. So both of my base values are going to be 0,5 minus 0,2. Let's put this one in here too. So it's going to be a half times 0,5 minus 0,2. Now I have to calculate the heights. The first one is going to be the height of this rectangle, and I'm quite fortunate there. I can see that that value there is 9,8, right? We see it? So I'm going to use that value because it's going to be 9,8 minus 0. So there's not much calculation involved on that one. This one, however, there is a little bit of calculation. This value I can see is 12,7, and I'm going to use the same 9,8 here. So this height of the triangle is going to be, other way around, is going to be 12,7 minus 9,8. Right, guys, I am going to switch back over to the PowerPoint and just give you the basics, but that's the easy way of doing it. And I promise you, sometimes they ask them, sometimes they don't. Best you know how to do them. Almost. There we go. Right, so in summary, if you have a position versus time graph, the gradient gives you instantaneous velocity. Velocity versus time graph, the gradient gives you instantaneous acceleration. The area under the graph gives you the displacement between those times. And guys, acceleration, there's only one thing we can do with that. We can go and calculate the area under the graph, and then it gives us velocity between two times. Right, guys, that brings us to the end of vertical projectile motions revision. I want you to now take some time. Go over organic chemistry, Newton's laws, momentum, and vertical projectile. Give yourself some time to study. And then in the next section, we are going to go and do a post-test. So again, I'm going to run through the post-test for you. Pause at every slide. If you don't have the post-test with you, do yourself a favor. Watch the video, pause every slide, try the post-test on your own. And then after the post-test, I will give you the memorandum so that you can go and see how your post-test and your pre-test compares with each other, and see if you maybe figured out a couple of insecurities and inconsistencies in your work. So go and stretch your legs, go do some studying, and I'll see you for the next session.
Wasametrics 2021 Catch-Up is brought to you by the Department of Basic Education, NECT, ETDP SETA, SABC, MultiChoice, and DBE TV on OpenView Channel 122 in partnership with